All right, so just a quick review. So we started last time. We are working on errors that you cannot avoid, and those are related in part to how do we store numbers on computers. So we went through integers, and last time we were talking about floating point numbers. And some of the main points are that in order to convert the number, you basically have to come up with the rules that are going to be followed. And one of those is that first thing that you're going to do with the number, you're going to have it in scientific notation. So basically you will have a number that is larger than, it's between -1 and 1, essentially. It could be positive, it could be negative, and times 10 to the exponent. That's a scientific notation. Okay? And basically when you will do that actually in base 2. Because our computers are binary animals. So in base 2, since you have to have a number that is sort of larger than 1, you will have a format 1 plus some number p that we are referring to as mantissa times 2 to the exponent. And now what you're storing mantissa, okay, you're storing p, and you're storing t in the computer. How do we do that? Well, we decide first whether we want to use 32 bits or 64 bits to store a real number. Those are referred to as single and double precision. And if you're, for instance, in single precision, you're going to use altogether 23 bits for mantissa. One of them is sine of the mantissa. The other one is just the actual magnitude. And 8 for exponent t. And if you're in double precision, then you're going to do 53 bits for mantissa. One of them is sine, the rest is the magnitude, and 11 for exponent. Again, one of these exponent bits is going to be sine of the exponent, and the rest will be magnitude. Okay? So basically, we actually went through then how upper limit is roughly to something to the 10 to the 307 or 8 in terms of what you can actually represent in terms of the largest number. Okay? But the simplest actually explanations was when we were actually dealing with the decimal system, then you would see that basically we had that with 1 digit, no matter what. Then your largest number is 9.9 times 10 to the 9, because those are the largest numbers you can squeeze into 1 digit. All right, so then this should make somewhat sense, no matter what. So we basically came up with what these numbers should be in terms of maximum and minimum that you can represent in double precision. That's 64 bits. Okay? No matter what, if you're representing a real number, you're going to have some smallest positive number that you can represent, and you can't go smaller. Okay? You can always represent a 0. So you do 0, and then this range that is in between a minimum and a maximum. And on negative side, you have the symmetric thing. So there is this largest negative number that is something very small in absolute value, but you cannot get all the way to the 0. And you have the smallest negative number that is something large in magnitude and negative. And if you're outside of this range, we call that overflow. Okay? So in magnitude, if you're larger than this if you're larger than this 2.23 times 10 to the, 1.8 times 10 to the 308. Okay? If you're larger than that, then you're in overflow. Whether you're larger, like where you're smaller on the negative side or larger on the positive side. And if you attempt to store, for instance, 10 to the minus 500, okay, that's too small. That's approximated as 0, okay, and that's called underflow. Most of the time, if you attempt to do that, computer will say, I can't do that, and it will do it as a 0. Sometimes it might actually just store some garbage. It's kind of unknown what it's going to do. All right.
And you can do the similar analysis for single precision. Then you're roughly on the 10 to the 38, so the largest exponent is 38, and the smallest exponent is 10 to the minus 38. And we have already seen that integers, this is a 2-byte integer, yes?
Oh, I was just wondering, is there a way to actually get an exponent bigger or smaller than 308?
What you could do, technically, you could basically say, okay, I'm gonna store just exponent as a real number, and then you would have a larger range. But that's almost never done. I haven't heard of so for integer, most of the time it's 2 bytes or 32 bits for integer, but these days there's long integer. So if you want longer integer, so that's going to be actually 64 bits for an integer, which can get to a pretty large number. So I've heard of long integers. I haven't heard of long double precision numbers. What ends up being, so for the most part, the benefit is not that great, and you would double the memory. So in a lot of applications, it's not that you cannot do double precision, but basically everything that you store, right? So let's say that you have 1,000 by 1,000 by 1,000 array of cells. That's not that much, 1,000 cells by 1,000. So let's say that we have a reservoir that is 1,000 feet by 1,000 feet by 1,000 feet. Right? That's not a lot. So that's 10 to the 9 of cells. If I'm just storing permeability for that, and I need real numbers. So let's say that I'm going with double precision. Double precision means that you're using 8 bytes, 64 bits, for each of those numbers. So suddenly, instead of 1 gigabyte, it's 8 gigabytes. Okay? 8 gigabytes, a lot of your laptops, that's your working memory is 8 gigabytes. So you can't even read it in, let alone plot it or do something with it. Okay? So now, so why then, and then permeability in petroleum engineering is not something that you know with the precision of 50 decimal points. You're good if you know the same order of magnitude, okay? You have a lot of uncertainty built into it as is. So essentially storing those numbers as doubles is already a waste of memory because you don't know them with that much precision. You don't measure permeability with that much precision. Let alone, so floating point single precision is plenty. And that saves you half of that 8 gigabytes. So at least you can store it or read it.
So I just want to try to figure this out a little bit better. The double precision is 64-bit, right? And you have an exponent that has 11 places, 1 for sign.
Okay.
So there's 10 total. And so if you add up 2 to the 0 plus 2 to the 1.
It's roughly 2 to the 10 minus 1.
Right.
The size of it, yeah.
What, is that 308 or is that?
It's close to 308.
It's close to 308. Alright.
So,
How did we get a 208 number?
so you have 11 bits to store the exponent in a binary form. What's the largest number? 1 has to be signed. Then you have 10 bits as the rest. Okay.
Just like 2 to the 0 add up to the 2 to the 10. That's gonna give me. That's only gonna be 0. 8.
2 to the 10 minus 1. Actually, no, it's gonna be 2 to the 1024 or something. So it's gonna be around. I did that calculation last time. So do it in. You have MATLAB open. Do it. So if I have 11 bits, what's the largest number I can store? Okay. And then if I wanted complex numbers, I would actually use 2 floating point numbers and look at them as a complex pair. So I would actually store both a and b, and I would understand that it's a plus ib, where I is square root of minus 1. Okay.
So, out of all of these numbers, if I have integer, 16-bit or 32-bit, what is the largest 32-bit integer that I can store? Can you quickly compute?
Side
Let's say unsigned.
or outside?
What's the size of it?
Is it 2 to the 22nd power because there's 23? It's a little bit.
No.
Are you talking about the mantissa?
I'm
or
talking
exponent?
integers. Let's review integers and real numbers are two separate animals. Okay, so just the integers, I don't need to have mantissas or anything. That's a waste of my time. So I have 32 bits. Let's say that it's unsigned integer, then all of them are just the number. What's the largest number I can store? 2 to the 32 minus 1. Is it? No. 2 to the 31 minus 1. So how many spots do I have? 32, right? And I'm going to start with 0, 1 in terms of powers, all the way to 31, right? If I have 32 of them. Correct? So 2 to the 31 plus 2 to the 30 plus all the way down to 2 to the 0 is 2 to the 32 minus 1 divided by 2 minus 1. Okay? So it's this number. What is this number? You have MATLAB open.
It's 3.1475 times 10 to the 9.
Okay, so it's something 10 to the 9. Can I store that first number?
Yes.
So even if I have signed integer, then I will just go half of this number in positive and half of it in negative, give or take. Okay? I will still be able to store a formula. Yes. Now, 16-bit number, what's my largest number if I'm signed or unsigned? So if I had 16 of these, the largest number here would be 15, right? If I had 16. And then here I don't lead with 31, but I lead with 15. So this is then 2 to the 16 minus 1. What is 2 to the 16 minus 1?
65,535.
Something. 232 or something?
Well,
530.
it is the same. Yeah, it's just 65,530.
Okay? Now, if this number was signed, okay, then half of these I can store as positive in terms of magnitude and the other half as negative, and I'm going to add one more negative number because there's that positive and negative 0, so one of them I'm going to assign. Okay? So is this in the range of the signed 16-bit? First one is, but this one, no. Because when you multiply by 2, it's something much larger than 65,000. And 60,000? I'm getting a whole lot of blank stares.
Quiz.
Questions?
Huh?
This is quiz.
This is the right way to calculate it, right? 360 minus
Yes.
Yeah.
Yes, it fits. So that's the 2 to the 6th minus 1. But if it was a signed integer, then I wouldn't go from 0 to 65,535. I would go to negative half of that minus 1 to half of it. As long as I have 65,535 values in there. Okay? Now for real numbers based on that table, is this something that I can do?
it's a real number, can I do this? Technically, I should convert this first to scientific notation. So it's 3 times 10 to the 404. But regardless, 404 is too large of an exponent. I can do roughly 308. Okay? Now, so I can't do this number in neither single nor double. I can't do it in double, then single doesn't have a chance. This number, can I do it in single? No, because roughly to the 38 or minus 38, those are the. So I can't do single, but I can do double. Okay. And this last one, I think it's right on the border somewhere of what I can do in single precision. Let's check. So single precision is minus 3.4 times 10 to the 38, 2 negative, and then this, so minus 3. Is it within? Okay. So let's just quickly see what happens when I'm doing arithmetic with these numbers. And actually, I think I'm gonna switch to writing. If I can find my notes. Yes, I can. So just quick comment on what happens when I'm doing arithmetic. Now, one thing with integers, okay? We know with integers that if we have 2 plus 2, that's 4, that's fine. But if I'm doing 51 divided by 17, and I'm doing integers, so if I can divide, that's great. Okay, I'm not gonna lose anything, but if I actually try to divide 4 by 3, and I'm storing it as an integer, it's gonna be chopped off down to 1. So that's something to be careful if you're working with integers, and your result is actually a real number. So then you should switch to working with real numbers. Again, MATLAB takes care of that by assigning everybody to be a real number, unless you specifically ask not to be. Now, in the real numbers, let me actually now switch to my sketchbook. Bless you. Okay, I'll just open a new one. 8. Okay. So if I was having arithmetic, okay, and round off errors, so essentially, first thing that can happen is, let's say that I have 0.36 or just 1.3641 times 10 to the 2 and 1.2686 times 10 to the 2. And let's say that I'm trying to do some subtraction here. So then the result is, if we're just doing, it's 0.0955 10 to the 2. And if I'm converting and storing that, I'm just pretending that I'm doing everything in the decimal system and that I have precisely 4 digits, right? So if I pretend I'm gonna fit that into the same format that I had, so it's gonna be 9.5500 times 10 to the 2. So essentially, there will be 2 zeros that kind of move in to fill in the space, if you will. Okay. So when you are subtracting numbers that are close, okay, then you're going to be kind of losing some of the leading digits. right? And you will have zeros filling in the space.
Now, what happens if you're actually adding or subtracting numbers that are very far apart? Okay, so let's say that I have 1.4 times 10 to the 5 and 1 times 10, just 10.
Yes.
How is that number the same? How is 0.0955 the same as
Soup. Good point. It's not. That's 100 times different. But if I'm trying to store it,
It's like, Dr. Zanich, you're trying to sell me some very odd math. It's not even, is it 10 to the 0?
I don't do math on Fridays, sorry.
My accuracy goes down.
Time for coffee.
Oh yeah. I actually didn't have coffee after lunch at this. I'm gonna blame it on that. Alright. So basically, but this is if I'm attempting to store it using the same type of principles, right? So just now pretending that I'm storing things in decimal system. Now if I actually do a similar thing and I look at these two numbers, okay, the problem is
That even if I had, I'm sorry, I'm missing also. Okay. So I have this system where I'm keeping only 4 digits.
just for kicks because I don't want to keep 53. Okay, it'd be difficult to show things. So the problem is that these are so far apart that if I add them up, okay, this one is actually here, okay? So if I add them up, it's gonna be, and you can
Exaggerate it even further. You can actually say, oh, or something of that sort.
right? So basically, when I add this to this number, I have to pick a common exponent for the two, right? So this larger number is gonna swallow the smaller one. Swallow in the sense that I don't have enough decimal places to actually make it show. Now again, this is not gonna be, these two will not be such a problem the way we store numbers now because we do have more decimal points than we're actually saving. But this is just to exaggerate what happens. It's easier to show these.
So the problem is that the final result, whether I'm adding or subtracting, the final result has to be shown in scientific notation with a common exponent.
And that basically cuts off the smaller number. So in itself, there was no problem storing this number. There was no problem storing this number separately. But the moment I wanted to do an operation that kind of made it into one number, now I have a problem. So I have, this is basically a roundoff during arithmetic. Okay? So it's because I'm actually doing something with these numbers. And you probably, what is the course where you get introduced to experiments and then they talk about decimal points and accuracy? Because a lot of instruments will have accuracy only physics labs. So whatever is the first lab that you do, you will go through these exercises where, you only have 4 decimals. So it's a similar principle. It's just the computer has 53 decimals, right? So that's not a problem. But still, nevertheless, you will have those errors happen, and they can occasionally pile up. So as long as they're not huge, again, there's that, depends on what we do, whether we
care about these errors or whether they actually show as important depends on what we do. So I had this very example at the beginning. The fact that I have double precision to store permeability is great, but it's a waste of resources because I can't measure it with that precision. All right. So this basically ends it. Save. So I can go back to my PowerPoint. So basically with floating point, first thing, I could also possibly, when I divide 4 and 3 initially, I had, so that's another example, I was able to store them nicely and fine, but then I divide them and then I have this 1.3333333, and no matter what, I gotta chop off some of these 3's. So similar thing, then when I actually try to multiply, let's say that this is as much as I could store, okay, and then I do further multiplication with it, when I do times 3, I'm going to have, instead of 4, it's going to be 3.999999999, okay? So essentially, mistakes will happen. Again, most of the time you will not necessarily notice because we do have quite a number of decimal points, but it might show up here and there that you actually see a number like this. Okay. So these are the then further these round-off errors that I just exemplified. Okay. They show up when we're adding and subtracting really small numbers to big numbers, or we are subtracting two close identical numbers. Now, one formula that you know really well that is commonly used is quadratic formula that goes like minus b plus minus square root of b squared minus 4ac divided by 2a. And depending what those numbers are, you will have both addition and subtraction. Okay? And often you might actually have addition and subtraction of a smaller number and a larger number, or subtractions of two numbers that are close. So actually quadratic formula has quite a bit of trouble with these round-off errors during arithmetic. Okay, so just to briefly review, okay, we are used to decimal system because we have 10 fingers. That's how we learn to count. Okay. So that's why it's stuck as a system of numbers, and that's using or representing numbers in base 10. We're so used to it we don't even notice. Like 158 means that I have 100, 5 tenths, and 8 ones. Okay? So that is basically representing the number in base 10. So I have a power 0 of 10, power 1 of 10, power 2 of 10, and so forth. Okay? We can actually play with all other systems, and the one that basically, so it could be base 8, it could be base 2. So how about you all do a quick exercise and convert 158 into base 8. So remember the powers of 8 are 1, 8, 64, and so forth, as well as base 2. Feel free to use a piece of paper. I'm just saying convert the number to a different base. I didn't ask to represent it on a computer yet. So it's just an exercise. You could be in base 8, for instance. That's not a computer base. Binary. Base 2 is the one for computers. digits in base 8. 0 through 7. On base 8, digits are 0 through 7. On base 16, digits are 0 through 15, except that for digits larger than 10, we use A, B, C, D, E. So 64 is my largest power of 8 that I can fit into this number. How many times? 2. And then whatever is left is 30. What's the next power that I can fit into it?
3.
8 is, power is 8 to the 1, right? And how many of them? 3, so my digit is 3. 3 times 8 is 24, what's left is 6. And 6 is 6 times 1. So it's 2, 3, 6.
So, but we're doing algebra in this on paper. How do we use the MATLAB to calculate this? Is there any quick way to calculate on MATLAB?
On MATLAB, I don't know that there is a function, possibly. I don't know the function. There's no direct function. But you can actually program it. So it's 2 times 64 plus 3 times 8 plus 6 times 1. That's 236 in base 8. And then a similar process would be for base 2. Okay. How would you represent 0.0054 on a computer? What would you do? You would find the format p times 2 to the t. Well, and actually, I was referring actually, so I'm gonna do this. 1 plus p and minus 1 plus p to be precisely similar to what we did before. Okay? So it's always a number that is larger, that is 1. So, or larger, so basically you would have it, you would then store only the portion that is different from 1. Okay? And you will, for this mantissa p, you will either use 23 or 53 bits to store it. One of those bits is reserved for a sign. And then t, exponent t, you would either have 8 or 11 bits depending on the precision. Okay.
Professor,
Yes?
the mantissa can be negative.
Yeah. So can I properly represent this number?
The exponents could be.
We learned the limits. The limits is around 308, right? So this is too much. Same thing with this. So in first case, I have overflow. In this case, I have underflow. Okay. And if you don't remember what these limits are, you can use int max, int min, real max, real min functions. So check it out quickly.
What exactly does int max compute? Like, what's the actual formula it's doing?
Precisely this. You just have to give it what size of an integer are you thinking. So int max of integer with 8 bits, you can do help on it to see this, but this is how you would use it, is 127. 16 And these are signed. And 32. So this is precisely what we went through here. These two we computed. So that's for integers because I have no decimal points to store. If you do help real min, you will see that you can use it for single and double. Okay? Single and double precision, so real min for single is this, and for double is this. So this is in positive, taken as positive numbers. And maximum is this.
So does that, when you type in max and min, is that giving you like the value before you tap it if you're going to compute it like using that equation over there? Or say if you have a sign in your byte?
Yeah, it's just, so the way it happens if you had that mantissa, you have 53 points behind the decimal point. So that's where that kind of not good looking number at the front comes from, 2.2 point whatever it is. Does that answer your question?
No.
So exponent is like an integer that you're storing, right?
Well, I would say like if you type in like int max of integer 8, it gives you 127, right? And then you type in 2 to the 7th minus 1 gives you 127. And you said like if we're going to find find actual min and the max values of that, you would divide that by 2. So
Okay, no. So review this part of the lecture. Where was it?
So if I had signed integer, right? 2 to the 7 minus 1 is 127. Okay? And then the range of integers that I could do if I reserve one spot for sign is minus 127 to 127. If it was unsigned, it would be 0 to 2 to the 8 minus 1, which is roughly twice this. It's 255. That's what I'm saying, roughly half it, because you're going by powers of 2, plus minus 1. Okay? So it's just that here we know that we can have a positive and negative 0. So there's no need to do that. So one of them will be mapped as minus 128. So the range of integers, if you do int min and int max of int 8, which is an 8-bit integer, you will get this. Okay?
So you would do that now even if you had 2 bytes or more bytes to store integer.
On the board, why is that 2 to the 16 as opposed to 2 to the 15?
Because 2 to the 15 plus 2 to the 14 plus all the way down plus 0 is obviously larger than 2 to the 15.
Yes.
And by formula is actually 2 to the 16 minus 1 divided. This is the formula I wrote 2 periods ago. All the way to plus x plus 1. It's x to the 1 power more minus 1 divided by x minus 1. When you plug in 2, this disappears because it's 1. Right? So any number here, just go 1 up, 1 power up minus 1 divided by x minus 1. Okay. If you need convincing, do x squared plus x plus 1 and times x minus 1 and prove it to yourself that it's x to the 3.
It wasn't that, it was just the first time we did it, we used 2 to the 31st minus 1.
Yes, so then I was scratching things off and just did both for 32-bit and 16-bit number.
No, I mean, we did 2 to the 31st minus 1 in the equation earlier. That's the number we got.
previously.
No, it was 32. I did it initially 31 and then I scratched off and then I did 32. I hope so I did that, but I think I caught myself. Because I started writing when I realized that if by doing it just by in my head I'm making mistakes. so that's when you start writing, okay? But this is the formula, okay? Okay. So basically, because of these precisions, okay, I will have some number that is so small that when I'm attempting to add it to 1, it's going to show up as 1, right? Because I don't have enough precision to capture both. So that's typically that number, I'm referring it as delta here, or epsilon m is machine precision. It's a number such that every smaller number that I attempt to add to 1 or any other number, it's going to be looked at as 1. Because essentially, I don't have enough storage to bring these two together on the same exponent when I'm doing the scientific notation. Okay. So that's the same example as I showed for those round-off errors during arithmetic. It's just that this number, epsilon m, we are referring to as machine precision. So as an exercise, how about you all create a script called find machine precision that finds this epsilon m reasonably close. You can't find what that precisely is. So we'll have to actually devise an algorithm to kind of get close to this number. So some sort of a loop that will give you smaller and smaller and smaller numbers, and then you will keep testing by adding that number to 1 until you get so small that when you add it, that 1 doesn't change. So think a little about it, try to kind of write down logic of it first, and then translate that to a function. And if we don't have time to work on that function, I want you to think about it over the weekend, and I'll ask you on Monday to submit it online. So.
Wait, not equal, is this squiggly line equal?
Different is squiggly, yes. Squiggly.
Not
Tilde.
squiggly line?
Yeah. Squiggly is called tilde.
Oh.
This is not equal. So then you have larger than or equal, smaller than or equal, and equal. So these are your relational operators. So this is going to be some kind of a loop, so you're going to have to initialize this delta as some number. Whether you want to call it epsilon or delta doesn't matter. And then you'll have to design a loop that will keep getting that number somehow smaller. And somehow can be up to you.
So like divide it.
For instance, you divide it with something and you keep dividing within the loop until,
It's so small that doesn't change.
so which loop is appropriate for this?
I'll do what? While?
While, because then you will check this.
Yeah.
If you do a for loop, you'll have to break out of it.
Can you start with a while? You don't have to use like for and while. Like you
No.
just start with
Start with a while. That's the whole point.
While?
Is this clear logically?
I.
So start with some delta of 1. 1 plus 1 is 2, so that delta is a good starting point. Okay? So that's definitely different from 1. And then I design a loop that keeps making that delta or epsilon smaller. I'm going to call it delta. So somehow, by dividing it by a constant number, by 2, by 3, by 10, by whatever you choose. Okay? And it's going to keep getting smaller in that loop. You
You're gonna just keep replacing your delta by delta divided by some number. And you will keep doing it, you will check whether 1 plus delta is larger than 1. If it is, you'll keep doing it. The moment it becomes equal to 1 or smaller, it's gonna stop. Does that make sense? So write it down as a script, or it could be a script or function. Either way, script is fine. I don't want inputs or anything, I just want it to execute. Find machine precision.m, and I'll ask you on Monday to submit it online, so work on it.
Do we need to specify like what format, like how many decimal places we need here?
No, that's decided by double precision. It's already in by the numbers. You could try to force it to be single precision. You could learn how to do that. You ask me questions. Curious. So get curious, right? You have to make sure that it's single. So force the numbers to be defined as single. That's what I do operation. Yes, I'll initialize it.
That's the thing.
Just say I is equal to 7. Just initialize it. Or no. It's going around, it's different from 1. So anything is different from 1. You're gonna change it. Just initialize it. For that matter, it's like 1 plus 2. I equals to 1 plus, but yes, 1 plus.
All we need to know is all I need to yeah. So I did 10 because 10 was like a decimal.
You're gonna be more active.
What is back?
Computer police. Computer police.
What that finds machine precision
Somebody use two, somebody use
so 2